without being the whole complete portfolio, but just to give you an overview of what we are capable of doing. We are manufacturers of the control valves, as you see in the top left corner. Then the system solutions, especially for heat transfer, steam terminal, where you transform steam to condensate and use the energy of the steam to heat your process or your heating purpose. We have steam generators, steam terminals, where we use thermal oil or also steam to produce clean steam, for example. Then we have system solutions for heating distributions, where we produce whole systems of heating distributors with control valves, with ejection valves. And as I mentioned, the absorption chillers in the 3 different sizes, the Bee, the Bumblebee, and the Hornet in the bottom right corner. Yeah, here just a quick overview on the control valves. They come in all different sizes. They come in different shapes. If there's anything that you would like to know about the control valves, also here, feel free to reach out to us. Here, just a quick overview on the types of control valves that we have in our program. We basically have 3 standard valve series, which is the BAELZ 340, the BAELZ 342, and the BAELZ 185. The BAELZ 340 as a standard 2-way valve, which comes in a steel housing. The BAELZ 342 also coming in the steel housing with the same housing basically as the BAELZ 340, which is a standard 3-way valve for mixing or sharing the media applications. And we have the BAELZ 185, which is our standard valve for condensate control applications used in steam terminals, for example, but can also be used for any other minimum flow application. Yeah, and as I said, all these components add up to system solutions, for example, for heat transfer, for steam, for thermal oil, for any other heat transfer application. And if you say now that you would like to see some of these system solutions or products in live, then you're always welcome to Heilbronn, to our headquarters. Just step by, give us a quick call up front or write us an email. And we are happy to welcome you in our showroom, give you a little tour, show you our system solutions, what we can do for you in terms of steam, in terms of thermal oil, in terms of any other heating or heat transfer application. Just reach out to us if there's maybe a day that you already know where you will be in the Heilbronn area, then step by and we can give you a quick tour. And with that, I say welcome to BAELZ. What I would like to point out is that you have the possibility to ask your questions in the chat. The 2 colleagues here from the technical side, they will write down the questions and hand them out to me. I will ask them to Andreas, and he will try to answer them live. And with that, Andreas, it's your show.
It's my power.
Yes.
Okay, thank you.
You're welcome.
So also welcome from my side. Hope you will enjoy it, and I will say something about steam water applications. The first slide, what I tried to show you is just a quick overview about the symbols in the steam technology, what it be used in the most of the time, like check wells, pumps, and so on. It's just for your information. You can read it down later when you have the presentation. Let's go first to the entropy of water and steam, and let's explain how this works together. First, when you have 1 kilogram of water and you will heat it up from 0 to 100 degrees, you have an energy get in there of around about 470.5 kilojoule. And when you heat up this water more and more in that atmosphere, you will evaporate the water, and you have another energy you would put into the steam of round about 2,258 kilojoule. If we look at these two pictures, you see the left one, when we heat up the water to 100 degrees, we call it sensible heat. And if you evaporate the steam, we call this latent heat. Together, we will have, when we heat up from 0 degrees to 100 degrees and then evaporate, we have together around about 2,675 kilojoule.
Yeah, it's just
Let's go quick.
that was quick. I know. Let me just interrupt you for a second because I think this is a very central slide. I think this is a very important point. If you could just go back to the slide. Yeah, perfect. So what is important is that we use the energy that is coming from the transfer of steam to water, right?
Water.
So when we use, or when we have the condensation process, when the steam gives up the energy and turns into water, this is basically what makes the difference, right?
Right, because in the steam you have more energy than in just hot water. That you see here, for example, 400 to 2,500. It's just much more. So the most energy we will get to heat up water or something else is in the steam.
In
so
the change of
the
phases.
change of the phases, of course, yes.
All right.
Thank you.
Andreas.
Let's see the next slide and just have a look about saturated steam and the different kind of in a different kind of pressure. When you see here, when you have 1 bar saturated steam, you have roundabout together with heating up to 100 degrees and to steam, to evaporate, you have roundabout 2,260 kilojoule. When you have 10 bars, it's much more, but the most energy there is here. The increasing of the energy is more in heating up the water because you need just more energy to go up to 180 degrees to evaporate the water. Let's have another look. What's for me very important to know is the volume of water and steam. If you have 1 kilogram and you will evaporate or you're heating up, the water will have around about 1 liter of volume. If you're heating up this one with 1 kilogram to 10 bars, absolute, you have around about 250 liters. You see the same mass have much more volume what it's need for the steam. That's very important for calculating steam pipes, for example. And when you go down, you see that for 1 bar absolute means atmosphere, you have something like more than the 8 times of the volume what you have at 10 bars. So what's very important is as near you're going to the atmosphere, as more volume you need for the steam. So it's not so important when you have high pressure steam from 10 or let's say 40 bars to 30 bars. The volume change is not this much, but if you're going from 10 to 0 bar, there is a lot of change of the volume. We have 3 types of steams. The first one would be saturated steam, means it's normally very dry. It's when you have evaporate the water, then you call it about saturated steam temperature, and then you have right on the phase change of the steam from water to steam. The next one would be wet steam, means this is the steam what you have when you see, for example, cooking water, and you see over the water bubbles, you see a fog. And that we call wet steam because you have not dry steam, you have some water in there. It's also saturated steam temperature, but this steam is wet because there's some water droplets in there. And the other one would be a superheated steam, means you have the steam evaporated and then you give more energy in there and that it's very dry and they have no water droplets in that, so we call it superheated steam. And next one. No problem.
Not to interrupt you, but I think it's
No, you interrupt me.
yeah, I do, but it's helpful for our audience.
Of course.
So forgive me
No
if I
problem.
interrupt you.
You're welcome.
You introduced the 3 types of steam. Which one is the one that we want to have for our heat transfer applications?
For the heat transfer application, normally you need saturated steam temperature because there is where the energy, the steam gives more energy to the phase change.
Yeah.
And when you have
earlier,
superheated steam in 10 degrees, you need first a lot of area to cool down the steam to saturate the steam temperature, and then so you want to have a nearly saturated steam temperature.
Yeah. So again, the most energy is transferred by the change of steam getting into water, condensating, and
in a different way. Also, the most energy you have to put in is from getting water to steam. Yeah.
All right, Andreas.
Thank you. Welcome. Let's see here a steam table to explain you how this works together with the liquid and the wet steam. On the left side, you see the liquid. On the right side, you see the steam, and between them, you have the wet steam area. For example, we're looking here 1 bar absolute. We have a saturated steam temperature with 470 kilojoule. Then we start vaporizing. That will be the 100 degrees. And after the 100 degrees, we're going from liquid to steam. We have 2,257 kilojoule. And when you put more heat in there, you will have overheated steam. That looks pretty simple how it works. And the different way you see on the top, you're going from superheated steam to condensation to liquid. Let's say something about steam valves, or let's say steam armatures. For us, it's very important when you use steam application to use ductile iron or cast iron for the valves, because gray cast iron is very brittle, and brittle means you have a lot of problems when you have some steam pressure drops or something like that. They can break, and they are not this soft like the ductile iron or the cast steel iron. On the right side, you see how we have to install a strainer in a steam pipe. I mean, the top one is very, very wrong, because in this one you will have not straining or not strain the steam. The middle one would be better, but would be normally used when you have water. But if you want to do it very correctly, you mount the strainer horizontal to the steam pipe. In case of when you're using the middle one and you have some condensate and you have some hammering of the steam, then the strainer can be break. So it would be very good if you're using the lowest installation for the strainer. And installation must be completely with the least pressure and PS class and the maximum TS of the steam. Let's go to the pipe dimension. Here on the left picture, you see a schematic piping when you have some condensate in the steam pipe. So you have a little small condensate on the bottom of the pipe. On the right side, you will have a schematic picture. You see when we have flashing or a lot of high water influence in there, mostly when you have a pressure reduction of hot steam condensate to a lower pressure, then you have a steam water mixture inside the pipe. So this is much more critical for the steam pipe as the normal condensate. Velocities in the steam pipe, what we normally prefer for saturated steam, because in saturated steam could be maybe some water droplets, would be good to have it between 20 meters and 30 meters per second. And if you go much lower on the saturated steam velocity, You have the influence of that you have more condensate because you are so slow with the speed. So it would be good to have them between 20 and 30 meters or 35 and or 10. So try to have this velocity. For superheated steam, the velocity could be much more higher because we have no water and nothing in the pipe. So we're going up to 45, sometimes to 50 or 60 meters per second because you have no issues with water droplets or condensate inside the pipe. So it would be good for the piping. If you have hot condensate where it could be some steam inside the piping, so it would be good to have not more than 0.5 meters per second or 1 meter per second. Don't go higher because you have some flashing, like looking on the right pictures. So steam water mixture is not good for the piping would be destroyed. I see I have another question
To you again.
again.
But there was a question coming from the audience that has to do with the strainers. So the picture that you showed, maybe you could just go back
Of course.
one or two slides so that we see the strainers again.
Yeah.
Yeah, here it is. So the question is, first thing is the fact. Comment says it's better, or it's good to see the better installation, but the question is why do we have to install the strainer sidewards? So is there a
That's
reason for?
Yeah, that's what I said in before. When you don't put it sideways, you put it down like the better version, and you have steam inside. Yeah, and the steam will condensate, so the steam will fall down on the lowest point on the strainer, and then maybe you're closing the pipe, and in 2 days or something like that, you have water inside and open really quickly the steam, and then you will hammering, and the strainer can be broke. And when you put it like sideways, like the correct versions, you have no condensate can be there, so the condensate can fall down on the next steam trap, so you have
Yeah.
no hammering and no destruction of the strainer.
And the strainer still works with that?
Yeah, of course, yes.
Okay.
I mean, with the wrong one, not because then you strain up,
Yeah.
but it still works and not the same. I mean, not this will be work. Let's say it like this. It's not
Works,
not
yeah.
not
Yeah.
200%,
Yeah.
a little bit less. When you have just water or very cold condensate, you can use, of course, the better version.
Mhm.
Then it would be better because of, but for steam, better using always in horizontal.
Because the condensate collects on the bottom, and if there's coming steam, the steam
And
comes together with the
with
condensate.
hammering, and maybe I saw some broken
Mm.
strainers already, so
Okay.
it's very
Yeah.
not nice.
Hope this helped. If there's any
Other
question
question?
left, just feel free to add it in the chat. Yeah.
Thank you. So where we are, where we are, yeah. So we was always finished with them. Here's some slides. The next 3 slides is just for your information how to install and what you have to check to install steam traps and how to install steam traps. Always be late falling. When you have always be late falling, the steam trap have to be on the lowest point, of course. The water will go on the lowest point. And the falling should be 1 to 200. And if it's not, if not if the flow direction is not defined, though you better use it a little bit smaller to mounting the condensate valve, the condensate steam traps. Sorry. Note for steam traps, and when we have that lot of water inside the steam, I already told you to have not a steam velocity over 20 meters per second. I see another question, so I will stay with this slide. No, no, wait a minute. Additional information. Another, give it back. Another information.
There was okay. The
So
question was not finished. Understand.
go ahead
Yeah.
and we will go back. Um, If you have a lathe with more than 1 to 100, um, um, should be the installation like showing on the picture, making a lowest point and strain it there. And here I have another picture when we have some up and downs and how they fall. And so it would be good to have when you fall down that the installation of the strainer would be less than 30 to 50 meters. And also what is very important to use eccentric line reduction and not diseccentric. Yeah, that's what the slide said. You can check it later to have it exactly. It's with good information for you. On this slide, I want to show you and try to say you when you're training a steam pipe, an extension must always be provided. So be sure that when you have, for example, a DN15, I rounded in the red circle, a DN50 pipe, that your drain or your extension on the bottom is minimum 500 millimeters and it's DN50, and then drain it from them. If you have a bigger one than 80 DN, you can smaller down the extension shown on this table. You also, another question, you have to go back?
Come in
Ready or not?
with my question. Yeah, ready or not? You have to. There was a question about safety valves. So,
Okay.
what about the PSV relief line velocities? So, I understood the question is about the media velocity in
After
this after the safety
after the
valve. Yeah,
safety valve.
when the safety valve
That's
is active.
That's a good question, and that is always there's a presentation from a lot of safety valve manufacturer where you can make an own presentation over that. So, but let's say it like this: when you have on the outlet, the velocity should be let's say the pipe behind the safety valve had to be as short as possible. So you have, and it should be not more than 90 meters per second.
90 meters per second. Okay.
Not more. Lower as better, as much lower as you have, and as much lower your back pressure are.
Yeah.
And that's good for the safety valves.
Here's something mentioned with sonic velocity, so 70 to 80% sonic velocity. If you just
That's
do
very
a quick calculation, I think that's something like 300 meters per second.
Yeah, and you can do it, but I prefer to have it as shortly as it possible, and I would do not more than 100 meters per second or something like that.
Yeah.
The safety valve manufacturer would say it's a little bit different, I guess. That's my experience, because when you have so a high velocity, you have a lot of back pressure, and that's not good for the safety valve.
Yeah, understand. Okay.
To work correctly. But this question have to be made to the safety valve manufacturer.
Yeah, I think also an own field where you can have your own presentation about.
Yeah.
And yeah, if there's any contact we should provide for a safety valve manufacturer, for example, just let us know.
Thank you.
Thanks, Andreas.
Let's have the next slide on the top. You see that we always prefer an eccentric than a concentric pipe reduction. You see it on the picture, of course. When you have a concentric, you have always, let's say, water or condensate who can stay there and can hammering on the steam pipe. So it would be better to have an eccentric reduction. Steam distributors must be always drained, that's for sure. And the next one is when you have water inside the steam and you want to have put out or tapping the point of the steam, what you have to put out of the steam pipe have to be always on the top, because then you can be sure that you not take the water with the steam. common expansion of pipelines. A very, very long theme to talk about normally, just for your information, is the extension is depending on the material and the temperature and not depending on the cross section and the wall thickness. So be sure you see that table that you make your bearings and your holdings exactly correctly, and for this and all piping manufacturers would be say something about that when you have to bearing and hold the pipe. I show you on the right side some examples to protect or to correctly mounting the bearings. You can have a look at that. Next question. Oh, that's very interesting. A lot of questions. I'm so bad, or
No, I think it's
so interesting.
It's an interesting topic you're
Of course,
talking about.
yeah.
Yes, we appreciate all your questions.
Of course, yes.
Go ahead with them.
Yes.
There was a follow-up question to the 100 meters per second of the safety valve topic.
Okay.
The 100 meters per second at which pressure? At set pressure or atmospheric pressure?
No, you have normally the safety valve goes to atmospheric, and that means on the atmospheric pressure. I mean, what you have in the pipe, what is going out of the safety valve.
Yeah, typically the line is going to
To a
the
silence
side of the building.
Yeah, and to a silence in normal case. In normal case, you try to mount a safety valve, and then you have a piping as short as possible, and then you go into a silencer.
Yeah. All right. Thank you, Andreas.
Yeah, thank you. Here I made just for you a practical rule of thumb, just an overview for you who's interested for. You can read down a little bit and get some information. That's just some rules to make it quickly to know what is what. And yeah, it's just an information, and you can check this out. On the next, what we see here is a schemata of a closed steam condensate circuit. On this R&E, I want to show you where we are. So I choose this because a closed condensate circuit is for BAELZ very normal. We have, for example, we're starting here with the water heating and process water and raw water heating. We're using our heat exchanger. There we are. The next one would be our clean steam generators would be used in this circuit. And then, of course, you need in this circuit some control valves. We have the regulator for them. We can regulate. We have different kind of actuators, like Michael already told you. So you can use all of our control valves with the controlling and measuring. The next would be steam conditioning. We have our 591 steam converting valve. I would say later on a little bit more about steam conditioning. So when you will see then more information. And then we have normal steam pressure control with in this case, with our self-operating valve. Could be also done with a normal control valve. And then we have also for the condensate handling, you need some instruments and systems we can deliver also. You see, we are all around the complete circuit, and when you go out on the steam and have the water heating, and so we have the heat, the chiller, we have the divider, and so we can deliver all the other parts on this secondary side also. Let's say something about steam transfer stations, what kind of design data we need. So we need the first one, the use case, for what do you need it for. Then we need the primary and the secondary medias, like steam or water, water. The design temperature and pressures, the maximum operating temperatures and pressures, what is handling on the heat exchangers. technical connections and conditions, and type and design of the control. Means you want to have a steam side control or condensate control. I will show you the difference now about steam side control and condensate control. On the left picture, you see the steam side control means you need a control valve in the inlet of the steam to control the temperature on the secondary side. And on the condensate control, you're controlling not the steam, you're controlling the condensate, where you controlling the outlet temperature on the secondary side. Of course,
Not with a question, but just to
make it clearly.
yeah to make it clear, because I think this is also a very interesting slide that you just
Yeah.
showed. Yeah, the steam side and the condensate side control. So we're making a difference between two types of controlling the power that the steam terminal provides to the secondary side. And
Yes,
on the steam side control, we control the amount of steam getting into the heat exchanger by a control valve on the steam side.
correct. And the condensate goes down, goes away.
Yeah,
Yeah,
yeah.
okay.
And on the other hand, we have the condensate side control, where we control the level of condensate in the heat. This is already
No, no, no. Okay, no, no. Let's do it with this slide. That's good.
yeah.
That's a good question. Yeah. And when we're doing the condensate control in, let's say in your words, your English is much better, to controlling the condensate level inside the heat exchanger, so
Yeah.
making more or less heat exchanger area for the controlling.
Correct. Yeah.
And the possible, I mean, you see it on this slide. Um, the disadvantage of a steam side control is that you have fast response of the control, and then means you have just more wearing of the components, because you have always a big heat on it.
Mhm.
And if you do it with a condensate, you're controlling the condensate because the steam is always on the top and it's not going less or more. So you're controlling the steam, the condensate level, and also of course we have more efficiency because a control valve on the bottom for the condensate is much cheaper, and you need no strainer on the steam trap on the inlet. You see on this left picture, we need another steam trap on the inlet of the
The condensate
heat exchanger.
Yeah.
Genau, yeah.
Yeah, so the condensate side control is the BAELZ standard.
Yes,
Because it's
more efficient,
more
more
efficient.
better.
Yeah,
It's a better
you
solution.
need less steam
They need
for the
less
Hemi.
steam.
Yeah,
It's the better solution. So we have this as a standard, but if the customer really want to have a steam control, we can do it, of course.
for example, for fast process
Yeah,
heating.
for example. Yeah.
All right, thanks,
Thank you.
Andreas.
So we always finish this slide. So good. Thank you, Michael, for that. Let's go on the next slide. Steam transfer station, steam water. Steam transfer, clean steam for clean steam generators or steam pressure reduction stations. We can do it as a complete unit. We have a lot of components we can use for it. So we are very specialized for doing this. We have this available power for a few kilowatts to several megawatts. So whatever is needed as a customer, we can handle this in normal case. No question. No, it's good.
Yeah,
it's good.
It's good that we have a lot of questions.
That's very good
that's what
that
we
you're
wish.
talking with me. So
Yeah.
I really appreciate.
Yeah, Andreas, the question is, do these work for regasification terminals? So we are talking about the steam terminals. I think the application is to when you talk about the LNG process, when you have the liquefied natural gas that you heat up again to make it liquid again.
Okay.
And Therefore, I think I can answer the question because we have done it quite a few times.
Yeah, right.
Yes, they are suitable for this kind of application. Basically, you use the steam from the primary side, use the energy, the heat, transfer it to the secondary side, and this heat can, of course, be used for the regasification terminals. Yeah, I know this application from a few projects we already had in Germany, but also can be used, yeah, internationally.
Thank you. Thank you that you answered my question.
You're welcome, Andreas.
Here, just make a picture how a complete or compact unit looks like. You see the inlet and the outlet connections, just for your information. The next one would be clean steam generators, where we put black steam terminals, the black steam terminal oil, hot water or electrical, and with the feed water is normally demineralized water or clear water, and we producing pure steam for that. This design can be horizontal or vertical, and the output is like the other ones, with around about a few kilowatts up to several megawatts, that we can all handle. Here's just a quick overview about our different kind of heat exchangers, and for what the applications are. Steam, liquid is the 105, and so on. You can see just a picture. I will say now something to the different kind of heat exchangers. We will start with the 105. It's a horizontal heat exchanger for steam side control, vertical for condensate build-up, controlling T2 constant, individual designs possible from large and vertical and so on. Materials is normal carbon steel. The tubes made of copper. Now I get it from the side, copper in English. Normal steel or stainless steel. We normally use as a standard the tubes with stainless steel. That's for all our heat exchanger because it's the best solution with costs and the heat exchanging. We can build this also in a fully design of stainless steel. The tubes are from 10 to 12 and a little bit bigger, with different kind of wall thickness. Go ahead. I got a question. Go ahead. Okay. The next one would be 106. Pretty similar to the 105, heating liquids, steam with large output range. We have accumulation from 0 to 100%, heating surfaces from 0.5 to 150 cubic meters, square inch. Sorry. Very compact design. The materials are the same with 105. I already explained it to you. The BAELZ bundle is a spiral bundle, tube bundle, made of 10 diameter of 10 millimeters. The next one would be our 111. It's a version for heating, water handling, process starters, and condensate in upright position inversions, including design possible for large, and the lengths can be also different kinds of lengths can be available. The materials is pretty similar to all the others. We can do this also in a stainless steel finishing also available. The bundles, it's also like the other ones, starting from 10 to over 12 to a little bit bigger. We have the heat exchanger 135. This one is an horizontal and vertical version possible. In this case, we have a shell tube side from 2, 4, and 6 way. So we have very compact design we can do. Individual designs is possible. It depends on your process data, what is needed. We will calculate one. The materials are pretty the same, no, the same like the other ones. And the tube bundles also from 10, 12 up to a little bit bigger. The last heat exchanger, what I tried to explain is our heat exchanger where we can have a modular system. You see it on the left side. This is one system for around about 200 kilowatts for at 5 bars. On the right side, you see the station, so you can put up into this this system different kind of these bundles, and then you can raise it up from 200 to up to 400, 600, 800, depends on how big you make the modular. Now you have it.
To let you finish the overview on the different BAELZ heat exchangers.
Thank you.
Just to sum up, if you're not sure which model is the best one to use for your application, just reach out to us and we can give you advice, technical advice,
Yeah.
which one would be suitable.
We will do it for you.
Yes. Another question that has to do with the condensate side control. Maybe you go a few slides back if that's not too complicated here. So that we see the, yeah, here for example. Yeah, this one would be perfect. Yeah. The question is it best practice to install a steam trap in series with the control valve?
No.
So we're talking, it isn't?
No, it's not possible. A steam trap, when you're mounting a steam trap, you see on the left side, then you make a steam side control.
Yeah.
Because when you're using a steam trap, you have always no condensate inside the heat exchanger.
Yeah.
So you're not controlling anything.
Yeah.
Means you have always 100% power of the heat exchanger. And though you were not controlling the
yeah, and it simply is not necessary. So
Yeah.
when you have a control valve on your condensate side control, there will always be only condensate. So
Yeah.
There's no pressure because there's a layer where there's the difference or the Übergang.
In English.
Yeah,
Transition.
the transition. Yeah,
Good.
yeah.
Thank you.
Thanks from the technical boys here in the background. Yeah, there's the transition from steam to condensate, and there will no steam be in the condensate line at the condensate side control.
No, it's not needed. And also we have some temperature sensors to check the temperature of the condensate to say, oh, no, the temperature is too high. We have some steam, so there is no issue.
Yeah, all right.
Thank you.
Go ahead.
Go forward.
Yeah. Few slides forward, yeah.
A few slides. Where we are. Condensate handling. We have a compact unit for the condensate handling in different kind of sizes. The next one, what is a very important theme is when you have hot condensate and you want to put it in a cold condensate, means hot condensate with also a little bit steam maybe inside. That's very critical because you have hammering, shock waves, and noise and vibrations. For this solution, we have our condensate injector cooler BAELZ 118. It is like, as you will see it on the next slide, much better. So you will have the hot steam coming from the right side inside the pipe so it's almost like a heat exchanger with open pipes. So you will go into the pipes with the hot steam condensate, and this hot steam condensate will cool down by the cold condensate, and the cold condensate will be heated up. So when you put it together, the temperature difference is not much so big, not much difference. So you have then a mixture of the hot and steam condensate without hammering, without noise. And it's a very good solution when you have to put hot condensate in cold condensate. Let's say something about the control valve configuration. For this, we have our our BAELZ valve selector, where we can choose the correct KVS values and the correct size of them with the velocities, and can offer to you. Here we have a steam valve for safety function. And you see here on the top, when we have to use a steam valve for safety function, means quick close by over temperature over pressure on the secondary side. We can use our valve 340. We have this kind of valve like already Michael said, in the standard two-way control valves with different kind of sizes from DN15 to DN300, different kind of pressure. We can do it in cast iron, in ductile iron, or stainless steel with balance plugs for smaller actuators. So it's in different kind of application or different kind of versions possible. The next one would be.
Sorry to interrupt you, Andreas.
Going back, I guess.
Just one slide back, just to make clear, so that there's no confusion about the control valve shown here on the screen. You have a three-way valve shown here for the two-way version, the BAELZ 340, as it's used as a safety valve or a safety control valve. On a steam terminal, there would be a blind flange on the third way. So this is the difference between the two-way and the three-way valve. They have the same housing, which makes more standardization. But you just use a blind flange to close the third way, but you can also use it as a mixing valve with the or without the blind flange.
If I remember really correctly, this picture shows a control valve with a positioner.
Correct.
But in normal case, we would put there, and you can have an electric actuator on it, for example, with safety positions, or you put there a solid valve on it. That's just a picture of the 340.
To be absolutely correct, I mean, this is what you said. The 340 valve, the steam valve, is just used for safety purposes. So when there's over temperature on the secondary side, the steam valve closes, and it has no control function because the whole control function is on the condensate.
When we do a condensate control,
correct.
When we do a steam control, we will use this kind of valve with this positioner.
Yeah, but if we do the standard BAELZ configuration,
it's condensate. Correct.
Control, yeah.
Let's go now to condensate control valves. This is normally our DN15 valve from our 185 valve. If the size, because I will show you in the next page, we have here the 385 is a compact design. We have small KVS values, like already Michael said. We can do some custom valve blocks. This has a stainless steel body and is only available in DN15 to DN40, DN15 to PN40. It is necessary that we have more condensate and more velocity inside the condensate on the heat exchanger than we're using our control valve 340. It's not limited. We have some special application. We can mount strainers and shut-off valve inside the valve of the 385. And if we put our element, the 206R on it, we can use this also as a self-operating control valve. The next example I want to show is a steam pressure reduction. Then we are in this case that we said, for example, we want to control the pressure. We're using our 340 valve. This reduces steam pressure to a set point of the controller. For here, you can see it from 12 bar to 0.2 bars. we have a steam designed to maintain the temperature minimum loss, a larger pipe diameter after the valve is necessary. Why is it necessary? I explained it a lot of slides before, that we have a large more volume of the of the of the steam. So in this case, we're going in with a DN 125, and we have to extend it after the valve to DN 200 to have a good velocity of the steam. Good.
Coming
Good.
from the audience has to do with the steam valve, the 340, when we use it for condensate side control. How would the steam valve ensure the safety function?
With normally with springs. I mean, if you're using here you can see a picture with a pneumatic actuator. With a pneumatic actuator, it's very simple because in the pneumatic diaphragma actuator, you have normally springs on it, and when the fail of the air is, the springs will closing, or you put it on the underside. You can open the valve also, but in safety valve, you want to close it. So this function of the safety function is already included. That no power to the valve means closing the valve.
Yeah.
For electric actuators, a little bit different because then you have to make a spring package on it to close the actuator, because electric actuator normally, when no energy or no power, they stays where they are. But in this case, when you put a springs package on it, you're closing the valve.
So it's automatically closed when there's no power, electricity, or compressed air in the actuator.
Correct.
And when is the valve closing? Closing at over temperature on the
Over
secondary
temperature
side?
or over pressure,
Yeah.
whatever you will be doing on your control system.
Yeah.
Yeah.
Or when there's no electricity or compressed air in the valve.
On the valve.
Yeah.
Correct.
All right. Thanks.
Thank you. Another question. I take it. Turn down ratio of the control valve. This is a good question. Depends on what kind of control valve. In normal case, we said depends also what kind of characteristic you have. If you have linear or parabolic equal percentage characteristic. In normal case, you can say for stroke, like what we use for stroke valves, between 1 to 30 up to 1 to 50. Depends on a little bit on the valve, but this is normally the turn down ratio, or yeah.
Give me that so you have free hands.
Yeah. Next one would be a pressure reduction with our self-operating valve 9192. Here it's the same thing what we have on the normal control valve. We need a higher or a bigger extension of the steam pipe, of course, of the pressure reduction and the volume. This has the let's say the advantage that you need no extra power from the other side. This valve operates himself. That means you just put it on a hand wheel or a little spindle on it, and you will see the different kind of pressure you can. How will you explain in English? Very difficult, but I try my best. When you come in with an inlet pressure of 12 bar, and then you have a manometer of the outlet of 3.2 in this case, then you will make the spring inside the valve to hold this 3.2 bar, and though this valve will be operated by himself, need no extra power. If you want to have a safety function, we can put an extra solenoid valve on it. This has to be electric, of course, and with this one you can have a safety function. Superheating or a superheated steam cooling with our desuperheater 591. Reduce the steam pressure and the vapor from the steam pressure and the temperature instead of reduction of the pressure, and inject water. Cools the superheated steam round about saturated steam level. And like we already had the discussion with Michael, it's always good to have saturated steam for the heat exchanger. So we can, when you have overheated or superheated steam, you can reduce them to your application, what you need for pressure and temperature near saturated steam temperature. Here's just a quick overview in what kind of sizes and how we do it as normally case. Another solution from our side about steam water application is our thermocompressor BAELZ 590 will be used for recirculation. Like the word already said, recirculation, we have one circle where we can increase the outlet pressure or the pressure what we have after the condensate flashing. And another one, when the compression means when we have an open steam, open valve, open vessel with, we have some other condensate coming in to increase the flash steam to a higher pressure level. Just here it's very good to explain. You see here our 590. We have here the flash, where you see on the top the safety valves come the flash steam. The flash steam will be increased with the motive steam to a middle pressure steam, and this can be used for our heat exchanger. So we really using the heat, what you're normally losing over the flashing of the steam, and goes normally over the roof. You're using them to heat up your secondary site on the heat exchanger.
Yeah, very interesting technology.
We have our own presentation for that.
Yeah, I mean, you could, of course, go a little bit or go a lot of more into detail, but I think the time is limited. And yeah, so therefore, we have another question from the audience that has to do with our 192.
92. Okay.
192.
Yeah.
The PRV, the pressure reduction valve. The question is, up to what temperature and pressure is the 192 available?
PN 40 to temperature, would say, I have to check it 300 degrees.
Something like that. Yeah.
Something like that.
We have to check our data sheet. Yeah, but that would be the.
I'm not sure at the moment. Sorry, not 100%. But in the data sheet it's written. But we have this up to PN 40.
Yeah. If you have more pressure or more temperature, we also have special valves that can also do.
Yeah, but not with the 92.
Not when
then you have to use a control valve, a normal control valve, to do this.
Correct. Yeah. Thanks, Andreas.
Thank you. Another question I take. How to avoid water hammering in the system? In what system?
Yeah, I think we would take this question, give some time to maybe get a little bit more into detail. Steam hammering. One thing that comes to my mind is to avoid water and steam, meaning condensate and steam coming together. You can use steam traps, for example.
That we already said about the 118.
Yes.
That's when we put steam water together, then we have, and otherwise we have no water coming into the steam hammering.
It depends on your system, what type of steam hammering you're talking about. I mean, steam hammering typically appears when condensate and steam come together, and the steam is taking the condensate with it and making it getting into steam again, and steam becoming condensate quickly. This is what causes the steam hammering. You can avoid it by using
that's why I said, for example, I mount the strainer in a horizontal.
For example.
That's, for example, there's a lot of different. It depends on what you mean with about system, what kind of system, and how.
When you have
when you talk about spraying into the steam, That would I explain to you later for the 591. There is no hammering. That would I explain to you later. Yeah. But if you have more questions, you can contact me and we can talk about it if you want to have this a little bit
More in detail.
more in detail. No problem. Thermocompressors. Yeah. The next one, where it's hammering, also a good issue, is there. What we here doing with our steam water mixture is we want to heat up water to spray or to put in steam. There we have a special valve, what is especially made for example, you have two 5-bar steam with a temperature of 180 degrees, and you have water with 20 degrees and 2 bars, and you want to heating up to around about 60 degrees, and you can put water, the steam right inside the water to heat them up. So you need no heat exchanger, but this is very critical, and this valve is very, very special. Now I want to close this area to heat and steam. Now I want to say something about steam conditioning or steam conditioning in temperature and pressure. I would say something about this, about the techniques to cool down and reduce steam. Where is this needed? I mean, this is needed, all everywhere in power plants, paper mills, chemical industry, breweries, all them need a special conditioned steam. We start first with the steam cooling, how we can cool the steam. We have two issues. We can just spray water in that, then we're just cooling down the steam. The next one would be we using a steam converting valve. This valve will be reduce the steam pressure and cooling down to spraying water inside the steam. You can do it, but also you can do it like a pressure reducing valve and install after them the superheater or something where you spray water into the steam. Where is this needed? I made just one example here, an example for in a power plant for a turbine. We have here on the red arrows showing the hot steam and high pressure steam who going through the turbine, and this one have to be needed to be reduced in pressure and temperature. Then we have here at the outlet the lower pressure and lower temperature. So we have at first our steam converting valve, so where we make a pressure reduce and a temperature reduce, and then we have the injection coolers or control valves for just cooling down the temperature, because the pressure reduce will be made in this case by turbine. Steam cooling technologies. What we can do is a fixed nozzle in two different ways. Here we see it as a ring, or just spray it over inside of the steam. The next we can do is a fixed nozzle with an integrated control, so you have not to use an extra control valve to controlling the water flow. The next one would be a variable nozzle, means we have just this different kind of nozzles with different kind of KVS that we open and closing. Another technology would be a Venturi nozzle and a spring-loaded nozzle would be also a technology. And last but not least, a motive steam cooler, means this one using motive steam to vaporize the water droplets, make it very fine. I just want to explain the different kind of cooling systems and what are they doing. First, we have the fixed nozzles. The fixed nozzles regulated by pressure means Lower pressure means lower mass flow, means also bigger water droplets. Higher pressure means more water flow and smaller droplets to cool down the steam. The next one would be variable nozzle. I already told you it's also over pressure, but in this case we have different kind of nozzle with different kind of KVS. So we can open and close. So the nozzles work always with the highest pressure drop and with the best spraying picture. The Venturi nozzles is working with the Venturi principle. So we have to, it's also over pressure, of course, but in this case, we're using the higher increase of the velocity of the steam to automation the water droplets. And the last one is the motive steam cooler. I already told you it's very fine automation because we're using the high pressure steam to vaporize the water. Just take like a summary. Fixed nozzles, when they use, when you have a rangeability or turn down ratio, it's also the same. You can use it also as a turn down ratio. We have here turn down ratio or rangeability of 1 to 5. It's also needed normally a thermal tube to protect the piping because the water droplets are very big. And the nozzle, and with a spring nozzle loaded, the rangeability would be a little bit higher. The next system would be Venturi system. We have here a rangeability of 1 to 10. It's for a good temperature control. It's okay. The Venturi nozzle creates additional turbulences, and effect of them, they cool down the steam much better than just a normal spray nozzle. And the biggest one or the best one is the motive steam cooler. We have a rangeability of the water of 1 to 50. Here we have the motive steam to vaporize the water, and we have at the outlet, let's say more like a fog instead of water droplets. So we have much more area where the steam can go through the water and vaporize them. So we have very small distance to the temperature sensor. We can go cool down very low to the saturated steam temperature. Here's just a quick overview about when you have steam cooling only. You can use fixed nozzle, variable nozzle, spring-loaded nozzle, or ring injection via spring-loaded nozzle, or motive steam cooling. If you have cooling with pressure reduction, we have a pressure control valve followed by a nozzle systems on the left side. You can have a steam converting valve with seat injection. You can have a steam converting valve with ring injection, or a steam converting valve with a motive steam head. Here I just want to show you the disadvantage and advantage. You can check this when you have later on this presentation. Different kind of, you will see that the different kind of systems have different kind of advantages and different kind of disadvantages. The same for the variable nozzle, how they are, the borders of them, and for the motive steam, the same. And here just want to show you real quick what you can read later, the disadvantage and advantage of the different kind of steam converting valves, in this case a ring, seat injection. The big disadvantage of the seat injection is that you will have maybe a high risk of thermal shock inside the steam, inside the valve. Then we have the ring, or the let's say the pressure reduction and the cooling after the valve. Here the big advantage is to put out the spraying out of the valve, so we have no destruction inside the valve. The next one would be our motive steam head. You can see that's only advantages, no disadvantages. This is a high-class cooling system where you can cool down really near saturated steam temperature. I make some tables real quick. with when you use what, you can have this and check it later when you have this presentation. It's very simple with the smileys. When you know what you want to do, you can use these two kind of tables. And last but not least, I just want to say real quick something about our steam converting valve 591, just for the advantage, what we're doing with them. You see on this picture, we have here two different kind of cooling systems. We're using the motive steam head and also in case of the protection pipe, what we install it, the Venturi system. So we have a very, very good ratio. We can go near saturated steam temperature and very, very low distance to the temperature sensor. From my side, I will be finished. It's getting a little bit long. It's getting a little bit longer than I thought, but you ask a lot of questions, and that's great. Thank you.
That's good. That's just the next question. Just pick it up, Andreas. Thank you. I also collected a few questions to ask, so that it's not getting too boring for you, just doing your presentation. We're staying at the steam cooling, for example, done by our BAELZ 591. The question is, at what distance from the ejection point do you advise to measure the required temperature?
Depends on what kind of cooling system you use. For motive steam systems, there is not even, you can say, half a distance of the steam pipe. That's what I've heard a lot of times. This is not correct. You have to check it, how much water you put in and what is the system you are. I would say minimum in normal case for our valve, would say minimum around about 3 meters. For normal injection with normal nozzles, with not motive steam, I would say minimum 7 to 10 meters. But could be also up to, depends on when it's a lot of water. For example, you want to spray 50% or 40% water into the steam pipe, then the steam needs much more time to vaporize the water, of course. Then the distance could be also 20 meters. Yeah. But yeah, depends on. It's not a question you can just answer like half a distance of the or steam pipe diameter. That's not correct.
Yeah. So long story short, this always depends. Come to us, come to Andreas, who will advise you when we have the project data. Yeah. Then another two questions that have to do with our thermocompressor, BAELZ 590. I think it's quite a few slides that you have to go back.
Go ask and I go back.
You go back. All right. Again, turn-down ratio. Which turn-down ratio can be accepted by BAELZ 590? And what is the guideline for motive steam pressure selection to low pressure steam? So the ratio between, you understood the question?
I guess, yes. Yeah. That's also a very good question. Depends also on the conditions. In normal case, the ratio is not this big because you have to suck the lower pressure with the motive steam. I would say depends on what is important for you also. Is your outlet steam important or what you want to suck important? It's also the question. I would say 1 to 5, 1 to 10, something about that.
Okay. But also individually.
Depends on when you have a higher motive steam pressure and you want not to go, the difference is not too high between the suction pressure and the outlet pressure is also an issue. Yeah. When this one is too high, this valve will be also not work.
Yeah, this was pretty much the second part of the question. So is there a rule of thumb you can say for the ratio between motive steam pressure and low steam pressure? So the steam you want to use for your application?
Very hard. When you have 1 bar to 3 bar is the other ratio. When you have 10 bar to 15 bar or something like that, so it's only 5 bar. So I would say very hard to say right now. We have to check. Also that's better you come to us and say, I want to have this and this, and then we say it works, or it could be not work, and then we have to make some decision.
Yeah.
Yeah.
Okay.
Sorry.
Yeah, another question having to do with the BAELZ 590. Does the steam being raised in pressure, so the low pressure steam, by the thermocompressor needs to be clean, or can we just use process steam?
Right. Have to be clean.
Has to be clean.
But it's normally clean, but because you come in, when you see the picture here, or let's say this picture, you normally come with the flash steam, or with the suction steam. You come in normally from the flash vessel or from the condensator.
Yeah.
So that's normally clean. Yeah. If you come from process, it would be better that you are using a strainer or something like that.
All right, and another question. I have to read it first. Where can we apply the steam operated pumping trap, SOPT, and thermodynamic traps? So steam traps that are also additionally operated by process steam to
Right,
put away
to
the
increase
condensate.
increase the condensate.
Yeah, correct.
You can.
Where can we apply it? Is there a necessity to apply it in our systems?
No.
Do we have to?
No,
Yeah.
normally not. But if you want to have this, we can do this also. But this is not a product from us.
Yeah. Yeah. I mean, can be used if you have low steam pressure or a high steam pressure loss during or going through your heat exchanger.
But
And,
normally using pumps.
Yeah.
Normally in case, because the steam is very, very, let's say, you have to pay a lot of money for steam, and you don't want to use them just to put up your
condensate back
to the pressure. You using condensate pumps.
Yeah.
They're much cheaper.
Yeah. Basically, in the most BAELZ applications, I would say they are not necessary.
No, and when we need it, we're using pumps.
Yeah. All right.
Perfect.
Yeah, checking.
Another question?
Okay,
my God.
are still writing.
We are not finished.
We are not done.
Okay.
Yeah, let me just change the questions here. Are they still writing? Yeah, maybe I can say a few words. Finalizing our presentation or our
I will go back.
Online seminar. Andreas, upfront, thank you so much for your presentation.
Thank you.
For your expertise here as an valve and steam expert here in our online seminar. I hope that you just enjoyed our presentation, that you learned something with all the questions that were coming. I think that you were also interested in the topic of steam, that steam still plays a major role in heat transfer systems. And yeah, we are very happy about all the questions coming up here.
Perfect. Thank you.
This is what we want to achieve.
Yeah.
Yeah, the question that I was waiting for is energy savings of 10 to 30% or more an exaggeration? For what system configuration, pressures, and temperatures were such valves obtained? Thanks. Were such values obtained?
I guess also the 590, I guess.
Yeah, 590 or maybe the condensate side control. For condensate side control, if the question was about that, I can say we have a calculation example where we compared the steam side control with the condensate side control, and we were saving 14% of steam just by using a different control method. And this is a lot. I mean, 14%. You can also calculate it by your own, or maybe we can do a calculation example, show you the difference. 14% in steam saving is a lot, depending on the power of the system.
By 590, also between 10 and 15% what we can saving. Depends on a little bit on the process data, but in the standard, it's round about them.
Yeah.
Yeah.
So it's no exaggeration,
Yeah.
by configuring a system that is energy saving, that is using flash steam that we would be going out of the roof and
Yeah.
für die Umwelt
To heat up the area makes no sense.
let the steam blow
Yeah.
out of the window. We definitely can make a difference by that.
Yeah.
And we should, because it makes you have our environment on the one side, you have cost savings on the other side.
And
So
the other thing is the customers or the people don't go there and say, oh, there's something going out of the
correct.
company.
Yeah.
There's something wrong.
Yeah,
No.
that's another thing. I mean, it's just visually you
Yeah.
drive by a company and you have
There's
the steam
something going
getting
steam
out of
out
the
and
window.
they're doing something wrong.
Yeah, correct. All right.
Yeah, perfect.
Any more questions from the chat?
Perfect.
No?
Good.
Yeah, I think this was the online seminar with the most questions ever, I think.
I never had this before. Thank
Yeah.
you so lot.
Yeah.
Really. I really appreciate.
Yeah. Also from my side, thank you so much for all your questions, for your interest. I hope that you enjoyed our online seminar. There will be more online seminars coming in the next year, also in English language again. If there's anything that you would like to know in detail when it comes to steam, when it comes to control valves, to heat exchangers, system solutions for heat transfers, or also absorption chillers, just reach out to us, to my colleague Matthias Peplo, who is responsible for international sales and also knows pretty much about the technical details. Or also Andreas,
You're always welcome.
feel free to reach out to myself or anyone else from BAELZ that you know. And with that, thank you so much for your interest, for your time, and see you maybe at the next BAELZ online seminar.
Have a great day or evening or whatever.
Whatever,
It depends on where you are.
Or afternoon, yeah, correct.
Thank you.
Thank you so
Bye.
much. Bye-bye.